Good morning, class. I see that people are still joining in, so let's maybe wait a few minutes, about half a minute at least, before we start. All right, let's get started for today. I want to start off with a quick reminder about this career expo that's happening tomorrow. It's for computing uh, students, but I'm not sure if everyone's allowed to be in it. But if you're interested, check out the Pathways Career Expo. You can find details about it at this URL, cs.utah.edu/pathways. It's not next Friday, it is tomorrow. Um, and, that's all I have to say about that. Just a set of reminders about homeworks and such things. Homework 2 is on Canvas. It's due on October 1st. And as of today, I think we'll be on track for you to handle all the questions in the homework. Please do use Canvas for discussion. I saw that there's a lot of interesting conversation there. And it's going to help with um, everyone figuring out what's going on. Um, and I wanted to remind you all about the project milestone. I have updated all the milestones for the project. I put submission things for all the milestones in the project on Canvas so that you can plan things ahead. The first milestone is on the 29th, which is next Tuesday, and it should not take too much work. It's about 15 minutes. All you have to do is click a link and register on Kaggle and upload a file and tell us your Kaggle user ID and the accuracy that Kaggle tells you when you upload the file. This should not take too much time, but it will just get you through the mechanics of how to get things on Kaggle and such things. So please do that. Uh, it will simplify things for us because the most important point of this milestone is other than the fact that it allows you, gets you access to the data and all that, the most important part is that we know what your Kaggle username is connected to your Canvas name so that it allows us to assign grades for project. And so it's like writing your name in an exam paper. In an exam, I mean, without the name, we don't know whom to give the points to. So please don't forget this milestone. So let's see if there are any questions. There's a question about average perceptron, but you found it in the assignment prompt. That's good. Is it accuracy, the score? I'm assuming this is about the project, right? Yes, it is accuracy. So I have constructed I've sampled the data so that the two labels are roughly equal. So I want you to think about the following question. If it just so happened that one of the labels was not equally likely as the other, would accuracy be the right way to score things? Uh, but that thought aside, for now, for this project, the score is the accuracy. It's the accuracy on the labels. That's right. Are there any other questions, comments, or reminders? Such thing. So there's a question about question 2, part 2. What I ask that you should justify how many mistakes the algorithm will make with a proof. What kind of proof are you looking for? Should this be a formal proof? Make it as formal as you can. Um, so it needs to be a reason, a line of reasoning that is not specific to an example. It should be something that um, the reader should know from what you've written, that you understand two things. One, that you understand what's going on, and two, that your uh, argument should hold no matter what the dimensionality is, for example, or without any special cases. So it should cover all possible cases. Now, uh, I value readability probably on at an equal level as uh, completeness. So please do make sure that it is readable. When you say, should this be a formal proof? I don't want it to be just a line of symbols with no text around. So make it, it should be complete, meaning every possible case should be considered if there are many cases, and it should work for all dimensionalities, and it should be comprehensible. The reader should understand it. Um, so the formality of the proof, make it, it doesn't have to be super formal, but it does not, you cannot, it should not be hand wavy either. There should not be parts where we don't know how you went from point A to point B because of some magic. Any other questions or clarifications in the homework? I'm going to wait 30 seconds for people to type questions if they have any. Otherwise, we will continue with where we left off. Okay, I don't, will I cover the least squares model? Yes, I will cover the least squares model after we finish Perceptron. So the plan would be Perceptron, then least squares model, least squares regression, least mean squares regression, and then we'll go to computational learning theory. All right, I don't know if there are any more questions. If there are, I'll come back to them. Otherwise, I'm going to go back to where we left off, wrap up mistake-bound learning, and then pick up on Perceptron. So in the last lecture, we looked at the halving algorithm. We looked at the mistake-bound model for learning. Just to remind you what the mistake-bound model is, uh, it's it involves the following things. It involves a protocol for learning where the learner doesn't rest. It essentially keeps receiving inputs. Every time it receives an input, it does two things. First, it makes a prediction. So every mistake-driven algorithm should have some component that's like, how does it make a prediction? The second thing is it doesn't. It possibly does a correction. If there is an error, if the prediction was wrong, after making the prediction, it receives the true label, and if that prediction is incorrect, it does an update. Now, how it does the prediction and how it does the update is left unspecified, and the question then is, we are counting under this model, how many mistakes can a learner make? So we define properties of concepts here. We define a concept to be learnable under the mistake-bound model if the number of mistakes it makes, which we call MA of C, it's learnable by some algorithm in the mistake-bound model. If the number of mistakes it makes for any sequence of inputs, even the worst case, is polynomial in the dimensionality of the problem. Now, if such an algorithm exists, we don't know if we may not know what the algorithm is, but if we can prove such an algorithm exists, then we say that the concept class itself is learnable in the mistake-bound model. In other words, if there exists some algorithm that makes a polynomial number of mistakes um, for any sequence of examples, then we say that the concept class is learnable in the mistake bound model. So in particular, we looked at this one proof of concept algorithm called halving. So the important thing to note here is the mistake bound learn. I can define a concept class to have a property. In this case, the property is it's learnable under the mistake bound model. I can define concept classes as having that property, but there don't have to exist any concept classes that satisfy that property. So in order to show that this is a non-trivial property, meaning there is at least some concept classes, first we will look at an algorithm, or we looked at an algorithm that we will analyze, namely the halving algorithm, and then start applying this algorithm to various concept classes to see if they are learnable or not. So the halving algorithm is a rather simple algorithm. It applies for finite concept spaces. So let's, as a cartoon example, let's say that I have um, 4 functions in the concept class, f0, f1, f2, and f3. These are 4 functions, and the goal of the learner is to find one of these functions. Maybe f1 is the true function, but the learner does not know that upfront. Every time a new input comes in, remember, the mistake-driven algorithm has to do 2 things. It has to have some way of making a prediction. It has to have some way of making an update. The prediction of the halving algorithm is the label of the majority of the hypotheses that are still under consideration. At some point, maybe these 4 may be under consideration. Halving algorithm asks all of them for their vote on the prediction, and then it takes the majority label. If the majority label is incorrect, what it would then do is it would remove all the functions in the set that are incorrect. Maybe so I'm not going to use continue this example anymore, but you can imagine how if uh, the majority of the functions are incorrect, then what we can show is, because more than half, but majority by definition is more than half the functions were incorrect. As a result, in the update step, more than half of them get tossed out, which means if there's an update, when does an update happen? On a mistake. So if there's a mistake, then more than half the functions will get tossed out. As a result, every single time there's an update, the size of the set of functions under consideration shrinks by half. It keeps shrinking by half, and that's why we call this the halving algorithm. And the we showed in the last lecture that halving makes no more than log size of the mistake concept class number of mistakes. So log size of C, order of that. And you should know this proof. You should be able to, this is a simple proof which you should be able to understand and reconstruct. Now, there was a point about optimality, which I'm not going to revisit right now. Let's now look at examples of how this mistake bound might be applied. So the first thing I'm going to do is let's say we consider the class of functions that are conjunctions. A conjunction, just to remind you, is a function that is a set of variables like this one here, connected by an AND. So this is a conjunction. And let's say here we also have negations are allowed. So the question for you to think about is, if I have n variables, how many conjunctions can exist? So for example, if I have 2 variables, then I have the following conjunctions. I have the function that always says true, the function that always says x1. X1 is a conjunction. It is a set of variables, in this case just one, connected by a conjunction. Well, there's nothing to connect, so it's just x1. X2 is a conjunction, x1 and x2 is a conjunction. But we also have negation. So we have not x1, not x2, x1 and x2, x1 and not x2, not x1 and not x2. So we have in all 1, 2, 3, 4, 5, and then 4 here. So 9 conjunctions. So the question, and this, I don't have a poll for this because I don't know how to make a poll with a descriptive answer. So feel free to answer it on chat. How many conjunctions would there be if there are n variables? So with n equals 2, we have 9 conjunctions. How many conjunctions would there be if you have, 100 variables or n variables in general? Does anyone want to? So there's one option, which is 2 power n minus n. So let me just write a few options. There's option 1, which is this. There's option 2, which is 3 power n. Does anyone want to? Oh wait, there are so many more. There's option 0, which is 2. What does star star mean? That I'm assuming that means power, right, in Python notation. So okay, so there is, it's the same. Is it? Yes. So there are a few answers. So t is a function. So if t is a function, so there's a question. If t is a function, should we not have f as a function as well? Now, I claim that f cannot be a conjunction because in general, if you, so think of conjunction as multiplying, and the uh, the the basic, the identity for multiplication is 1. The identity for conjunction is true. So you take an and with true, the function gets preserved. You take an and with false, it gets destroyed. So the identity, so if I ask you to list out all polynomials, so in general with polynomials, you have x power x1 power 1, x1 square, maybe, and things like that. But there's also x power 0, which is equal to 1. And that's what true is doing. You don't put 0 there as a polynomial, and conjunctions behave in the same way. So there are a few answers. There is 2 power n minus n, and then there is one more, and I'll stop with this. There's 2 power n plus 1 plus n. Did you make this fit for 9? I think. No, it doesn't work for 9. But let me, so these are all useful answers because I want you to think about this carefully. This is the kind of thinking that we'll also be looking at when we come to computational learning theory. Essentially, because learning is search over functions, the size of the search space is always going to matter, no matter how you formalize learning. So this is one of the first exercises of that kind that we are encountering, but we'll encounter this more often. So the number of conjunctions, I claim, is 3 power n. And let's see why. Okay, so there are n variables. What is a conjunction? A conjunction is a function that has a bunch of ands, something like that. And let's put empty slots in between. Now, let's put n slots of this kind. Now, each slot can be filled with either the variable x1 or its negation or just true. There are 3 options here. Similarly, this slot can be filled with x2, not x2, or true, and so on. The last one can be filled with xn, not xn, or true. So every slot has 3 things we can choose from. I could choose x1 here, true here, and xn here, and true everywhere else. And if I choose x1, true, true, xn, then I get the, or let's say I put not x1 here. Then I get the conjunction not x1 and xn. So every conjunction can be constructed in this way. What that means then is the number of options that we have for constructing these conjunctions is you have 3 things that can go into each slot independently of all other slots. So you have 3 things here times 3 things here times 3 here times 3 here. And there are n possible slots, so you get 3 power n. So why don't we include so this is there are a few clarification questions. Why don't we include false as one of the options? Let's think about what happens if you include false as one of the options. Let's say I put a false here. And let's say I put a false here, and I can put anything else. Let's say I put x2 true, x3 no, x4 here true, xn. Now because I have a false here, remember false is like multiplying with a 0. If I put false here, the whole function vanishes because false and anything is false. So false is not a conjunction. As a result, we will never include false when we are trying to build conjunctions. When we are trying to build disjunctions, however, when we use an or, we need to have false but not true. Disjunctions are like addition in that sense, in a loose sense. So adding with 0 does not matter. Multiplying with 1 does not matter, but adding with a 1 changes the value. Adding a 1 changes the value, and multiplying with a 0 changes the value. So if we had a false here, then the whole conjunction vanishes and the conjunction doesn't exist anymore. So we don't include false because it's not a conjunction. So there is another question. Can I explain the difference between xn and t? Is it specific to xn, or is it for so any x? Okay, so t is just the constant true. So essentially, instead of t, let me explain this in a different way. Okay, let's say that instead of t, we have the following. At every position, I can say maybe an x1 can go here. Let me erase everything and redo this in a slightly different way. Hopefully, this will remove both these confusions. I can either put an x1 here, or a negated x1 here, or I can decide that x1 does not belong to this conjunction. The empty set means no x1. This symbol here just means x1 is not there. That looks weird, so let me just put a dash. Basically, you're passing on x1. I can put an x2 here in the conjunction. I can put a not x2 in the slot, or I can just pass on x2. Similarly, I can put a xn here. I can put a not xn here, or I could say xn is not in this conjunction. The true is just serving as a way of mathematically correct way of setting that up. But really, it's just saying, let's consider the conjunction x1 and xn. What we have done there is we have chosen x1, we have chosen xn. For all the other slots, we have passed on that variable. We have said, that variable is not there. So for every slot, there are 3 possible choices. Either the variable shows up, the variable shows up negated, or it doesn't show up at all. And doesn't show up at all can be written formally as true. But if that's confusing, we can ignore that. I'm assuming that the function we are looking for f is true. I don't assume that at all. I don't know what the function we are looking for. We are trying to construct every possible conjunction. This is a procedure that constructs every possible conjunction and only them. So now that we have constructed all these conjunctions, we know that the number of conjunctions is 3 power n. Now we can ask, what would halving do? In the worst case, halving is a worst case bound. In the worst case, what halving can do is it would make log size of c mistakes. In this case, size of c is order of n. What this is a statement that says the halving algorithm will, so log to the base 2 of 3 power n is something. It's a function in n. So the next there's a clarification. In the example shown, x2 and x3, x4, x5, and x100, if those values are correct, then it doesn't say what x82 is because x82 is true. That's right. So coming back to this thing, what is the statement saying? This says the size of the concept class is 3 power n. And the halving mistake bound says that the number of mistakes is order of log size of c. That just says that halving will make no more than order of n mistakes. So the number of mistakes is, in some sense, I should not write less than, is equal to order of n. that means the number of mistakes will be less than some linear thing, order of n thing, uh, polynomial, but no more. It will not make, say, n square mistakes. It cannot make n square mistakes when you're learning conjunctions. What this means is, remember, halving is a conceptual thing. Halving is not a real algorithm. It just says there exists at least one learning algorithm. It's an upper bound. Halving is an upper bound on the number of mistakes. There exists one learning algorithm, halving, which will make at most order of n mistakes. It's a pretty lousy algorithm because it is extremely inefficient. Remember, for halving, you need to enumerate every possible function, and we're not going to do that. If I find out at any point that one of you is trying to implement the halving algorithm, I'll be a little sad because you're trying to enumerate functions. That's not going to work. So it's just saying that there could exist a function, a learning algorithm that can learn conjunctions. The next thing to think about is there an efficient algorithm that realizes that bound? Halving says there is a potential to reach the bound. Is there an efficient algorithm that realizes the bound? We've already seen an efficient algorithm. We saw this algorithm called elimination that realizes the mistake bound of halving. If just to remind you, this was the slide that described elimination last Thursday, where we just, every time a feature value is 0 in a positive example, we eliminate the feature from the conjunction. And we showed that this will make no more than or n mistakes if you have n examples. So the elimination algorithm is an efficient algorithm that realizes the mistake bound that the halving algorithm promises. Let's look at another function, which is k conjunctions. A k conjunction is a smaller set. It's basically saying you have k features. There are n features, n variables in all, but every function in the set has no more, or let's say exactly, not no more, but exactly k of the variables, and you take a conjunction of them. Okay, potentially negated. So you could have, for example, a 3 conjunction would have x1 and not x3 and x17, but it will not have x1 and x3 because there are only 2 variables here, and it will not have x1 and x2 and x3 and x4 because there are 4 things here. So these 2 are not allowed, and this is a 3 conjunction. So once again, the game is the same. We need to count how many functions there are. To count how many k conjunctions there are, this is a neat trick. What you do is notice that a k conjunction requires you to first decide on which variables need to be participating in the conjunction. So you have 3 conjunctions. In this case, you need to pick 3 variables. If you have k conjunctions, you need to first pick k variables. So how do you choose? How do you select k variables out of n things? You have n variables in all. You have a bucket of n variables, and I need to pick k. How do you pick? In how many ways can you pick k variables? It is n choose k. Now, once you have chosen these k variables, let's say I have chosen x1, pick k conjunction means exactly k. So let's say I have chosen x1, x3, and x17. And I'm going to put a conjunction in front by connecting them. I still have a choice. Should this variable be negated or not? So either it can be negated or not negated. And this exact same 2 choices, these exact choices also show up here for x3 and x17. So once you have chosen 3 variables, you can choose to negate or not each variable. So there are 2 options for each of these k variables, and that's why you get 2 power k. So 2 power k and choose k is the number of k conjunctions. So the important thing here, and this is the next thing I was going to bring up, there's a question that says, can the variable be set to true like in the conjunction case? Notice that here there are only 2 options. So essentially here, instead of saying negated and not negated, the options are either I can Either I can have x1 or not x1. Here I can have x3 or not x3. And here I can have x17 or not x17, but not true. The reason is I'm not allowed to skip the variable. I have already decided to pick these three variables, these k variables. Once I have decided to choose them, putting a true in the list of options means after choosing the variables, I'm throwing it out. But that's not allowed because I've already committed to these things. So here I've only got, I have to, once I've chosen these three variables, I'm forced to either keep the variable as it is or negate it, but I'm not allowed to toss it away. So in that's the game. That's how the k conjunction is defined. And in that case, the number of k conjunctions is 2 power k times n power n choose k. So let me erase this stuff so that I get a little bit more space. Now I claim, and I'm not going to answer this now, but I claim a very, very loose approximation of this is 2 power k n power k. And I would like to let you think about why this approximation is at least reasonable. So now the game is the same. Once you have this, we have the number of functions is order of 2 power k n power k. I need to take the log of that. So log to the base 2 of 2 power k n power k is roughly order of k log n. So for learning k conjunctions is the number of mistakes is less than the number of mistakes for learning just conjunctions. So you have conjunctions, the number of mistakes was order of n. Here is order of log n. The question to think about is, sure, this is just a proof of concept algorithm. Can this be realized efficiently? And let's maybe talk about that in a little bit. But let's see if there are any questions. In the homework, the question is at most k. It's not exactly k. That's right. And the conjunction, the keyword to knowing, wait, is conjunction the keyword to knowing you can choose a negated variable? How do you know when we are choosing negated variables or not? That's usually told in the definition of the function. So if I say conjunction, usually it is negations are allowed. If negations are not allowed, the name of the set would be monotonic conjunctions. So whether your negations are allowed or not, you would know from the definition of the function, one way or another. So, okay, so this is like the general procedure for thinking about functions, function spaces, concept classes. An exercise that I would like for you to think about, I didn't write it in the slide, but I want you to think about is what happens if I want to learn if the hidden function is any Boolean function. The procedure is the same. First, you need to find how many Boolean functions there are. So it will be 2 power n, and we have covered this a few times, so I won't revisit this right now. And then you take the log of that. The log of 2 power n is still 2 power n, which means any Boolean function, if I tell you that the hidden function is some Boolean function and I don't have any subset, the number of mistakes is exponential in the dimensionality. The number of mistakes is exponential in the dimensionality means it is not polynomial. These two are polynomial. So that means arbitrary Boolean functions cannot be learned in the mistake bound model. We already have a negative result. The mistake bound model is such a simple model, and yet it allows us to show that the claim that I made in maybe the second lecture, if the function space is any Boolean function, learning is not possible. And here is a formal way in which we proved that. We can do that again. We will do that again when we talk about learning theory. So there is a question: how do I have n power k in the example? So I claim that 2 power k n choose k is approximated. If a more correct statement would be less than 2 power k n power k. And there's an easy and dirty way of proving this. What is n choose k? N choose k is n factorial divided by k factorial times n minus k factorial. And If you remove the n minus k from the top, you get n times n minus 1 times n minus k plus 1. How many terms are there? So this is, okay, I feel like I should not be writing on top of text. So let me just, so n choose k is n factorial times n minus k factorial divided by k factorial, which is, I'm going, oh, what have I done here? This is totally wrong. Divided by k factorial times n minus k factorial, which is n times n minus 1 times n minus k plus 1 divided by k factorial. Notice that every term here in the numerator is less than n, less than or equal to n. That means n choose k, loosely speaking, is order of n power k. And that's why I get the n power k in this thing here. But if you want a more formal explanation, then this is, you'll think about it offline and we can chat about it later. Can you use this in the homework? Yeah, you can use this in the homework, yes. Any assumptions that you make in the homework, please state it cleanly, because that makes the thing more concrete. All right, now let's think about let's maybe think about this question here. Can we learn efficiently with, is there an efficient algorithm which learns with these many mistakes? And for that, we need to think about representations of functions. What's the best way to represent functions? Oh, there's a question about homework. The homework doesn't mention negations. I wrote about this on Canvas. The short answer is for the XOR functions, pretend there are no negations. I think that's what you're asking about, right? But it's worth thinking about what happens if there are negations. It's actually an interesting exercise. So assume you want to learn conjunctions or k conjunctions. The concept class is a k conjunction. Should your learner also be exploring this concept class? So this is a set of conjunctions. The question is, should your learner be searching this set? Should it be searching another set that overlaps with it? Or should it be searching another set that contains it? And why should this question even come up? The question comes up because of this somewhat discouraging theorem from David Hausler in 1988. If you have a data set with n features that is consistent with the conjunctive concept, meaning the concept class is a conjunction, then it's intractable. It's NP hard to search for if you search in the space of conjunctions, it is intractable to find the search problem is intractable if you want both a consistent conjunction and one that has the fewest, uses the fewest number of features. This is essentially saying, if I care about the smallest hypothesis that fits the data, finding that smallest hypothesis can be computationally intractable. This is true for disjunctions also. But there's, if you care more about how to do this, the proof goes by a reduction to minimum set cover. But that's not the point here. What this means is we cannot learn the concept efficiently and with the minimum number of features if we are searching in the space of conjunctions. But we could do it, and we will see that we can do it if we are willing to expand the search space to be any linear threshold function, any linear classifiers. So remember, every conjunction can be represented as a linear classifier. So if this is a set of conjunctions, set of linear classifiers includes conjunctions. This is LTU, this is conjunctions. It includes conjunctions, it includes disjunctions, and other functions also. So what this theorem is saying is, if you are going to search in the space of conjunctions for a conjunction, it might be hard to find. But if you expand the search space, the search becomes easier. And this is, if this result doesn't bother you, you were not paying attention. What it's saying is, I need to find something in a certain space. And in order to find it in that space, I'm going to look for it in a much larger region, and it will be more efficient. Essentially, expanding the search space makes search more efficient. And this is slightly non-intuitive. This is true even when you know that the true function is a conjunction, if I want to have the minimum number of attributes in question. And the reason for this is because the conjunctions and disjunctions and such things are combinatorial spaces. Combinatorial optimization can be much harder. Linear threshold units allow us to play with real numbers, and real numbers give us more room, so to speak. In the set of linear classifiers is more expressive. And as a result, the search for a good hypothesis can be more efficient, even though we are searching for a combinatorial function. And this is one of the reasons why, even though we will be using Boolean functions and discrete functions for constructing the theory, anytime we want to come to practical learning algorithms, we'll be quickly moving to these sort of continuous functions or functions in that involve real numbers. So what do you need to know as far as this particular unit is concerned? You need to know what's the mistake bound model, what's the definition of a mistake bound function or mistake bound concept, for example. You need to know about these proof of concept mistake bound algorithms. The algorithm called con makes order of size of C mistakes. You need to know why. Halving makes log size of C mistakes, and you need to know why. Neither of these algorithms are efficient because they essentially don't care about either storage or computation time. And then there is this last, you need to know how to apply these bounds for these simple function classes like you're doing in your homework. And finally, you need to also know this fact without any proof that even though we have all these nice results with discrete spaces, learning them with linear threshold units can be computationally easier. Okay, I'll pause now for questions while I drink my tea and pull out the next set of next lecture involving the perceptron algorithm. I don't see anyone asking questions, but by the way, I would encourage, I noticed there's something that's intriguing that's happening with this online medium also, which also happens in an in-person class. Um, People kind of get comfortable with not speaking in an in-person class. So the same set of people ask the questions and answer questions. And in person, what I would usually do is I would insist that someone who has never answered in class answer the question or ask a question. Um, it's a little bit more awkward to do that online, but I would encourage people to participate, ask questions, because it makes the class more lively. And also it ensures that even though if you feel like you have not understood something, I guarantee there are others in the class who've not understood, so you'll be doing them a service as well. Um, a side effect of asking questions is that we slow down a little bit, but I think that's okay. The goal of the class should not be, I need to cover as much as possible in the time that we have. The goal of the class should be, you have the basics as clear in your head as possible so that if necessary, you can pick up the rest. So I'm more concerned that you get the basics right. So please feel free to ask questions. Participation is always useful because otherwise, in the absence of signal, I can't see your faces. So I don't even know, I don't have the social cues to pick up on whether you're confused. So please do help me out there. We can't linearize all functions. So there is a question. We can't linearize all functions, for example, XOR. But is XOR a conjunction? And so the question continues. I understood you to mean that we can turn any conjunction into an LTU, but what's missing? XOR is not a conjunction. Let me give you what I mean by that. So let's take XOR. So let's write down a definition of it in 2 dimensions again. X1, you have 2 dimensions, X1, X2, X1, XOR, X2. I don't like using a symbol for XOR because it's not universally accepted. So the XOR function might be something like this. This is not a conjunction. The reason this is not a conjunction is because, well, you can prove that this is not a conjunction in different ways. I'm going to just prove it to you by writing down the function x1, x or x2 is defined to be x1 and x2 or not x1 and not x2. Oh, let me write it in a, yeah, this is fine. It's an or of two conjunctions. Did I get it exactly wrong? Yeah, I did. So I wrote x nor. So let me write it x1 and not x2 or not x1 and x2. It's an or of two conjunctions. Either x1 is 0 and x2 is 1, where this thing is true, or x1 is 1 and x2 is 0, where this thing is true. And the or of these two things is the XOR. As a result, XOR is not a simple conjunction. So as a result, we cannot, the points, everything I said about conjunctions does not hold. There's another question. If I want to learn conjunction, your hypothesis space should not be a conjunction. Yes, isn't that weird? This is especially true of K conjunctions. K conjunctions are interesting because the mistake bound is K log n for halving. But the efficient algorithm that realizes this mistake bound uses a linear threshold unit. Expanding the search space makes the search easier is a slightly non-intuitive concept because what happens is if I'm searching over a discrete set, I have to essentially, so in general, discrete optimization is can be more difficult than continuous optimization. For example, with continuous I understand that we haven't spoken about the optimization perspective of machine learning, so I'm being a little vague here. You can think of learning as an optimization problem. It's searching for the best classifier, however you define best. So if you're searching for the best classifier in a discrete space, it's a discrete optimization problem. If you're searching for it in a continuous space, you have a continuous optimization problem. Now, the reason continuous optimization may be computationally more efficient is because you can use things like gradients, you can use calculus, you can use derivatives to perform the optimization, to kind of navigate the search space. If you're going through discrete, if you're doing discrete optimization, we don't have that. We do not have that one important tool, namely gradients. And as a result, search becomes harder. This is not really, everything I said is just an intuitive thing. There's nothing formal about it, but the tool that we will use again and again, starting maybe in the second half of the class, is the notion of taking the derivative of functions. That fundamental tool is not applicable to us when we are in the space of Boolean functions or discrete functions. Is there a vacuous case for XOR when we cannot choose any variables? Yes. Let's see. This is a good question. I haven't thought about it. I'm going to say yes. The vacuous case is, oh, okay. So yeah, false is the vacuous case for XOR because adding a false does not change the parity. Adding a true changes the parity. And so that's the vacuous case. So there's two more questions, and then I'll go back to Perceptron. Using OR means our function is not a conjunction. That's right. Yeah, well, using an OR by itself, yes, it's more than that. There is, in this case, there is an OR of some AND. So it's not a conjunction. But even if I have just an OR, x1 or x2 or x3, it's not a conjunction. This is a disjunction. So using an OR automatically would mean that our function is a disjunction. What learning protocol are we using? We could learn conjunctions using exactly n variables. Yes, we can learn conjunctions with n variables, but the theorem of Hausler goes more than that, says more than that. Not only is it learning the conjunction, but uses the fewest number of features in the final result. We want to find the result that we had only talked about consistent. So we can find a consistent conjunction with or in order of n time. We cannot find a consistent conjunction that is the smallest one in if you want this Occam's razor style extra. The example that we saw showed this thing where in this, so let me zoom in on this. In this case here, notice that the smallest conjunction that's consistent with all the examples is just this. We had this extra straggler that came along, and finding the smallest conjunction that's consistent with all the data would not if you had found it, you would not have had that x1. X1, this h on the screen is some function that is consistent with the data, but not the smallest one. And the Hausler's theorem talks about the smallest one. All right, so in the half an hour that's left, I'm now going to introduce the perceptron algorithm and then talk about some variants. So let's talk about the perceptron algorithm. So the perceptron algorithm is an algorithm that learns linear classifiers. So let's just quickly revisit what a linear classifier is. A linear classifier is a function which takes n-dimensional or d-dimensional input vectors. So we'll use bold letters for vectors, and produces a label which is a -1 or a 1. It classifies an example using a weight vector w and a bias in the following way. It first takes the dot product of the weights with the example, so that is w transpose x, which is simply the sum over all the features of wi times xi for the ith feature. Now that's a number. Then it adds the bias, so you still have a number, and it looks at the sign of that number. And if the sign is if the number is positive, then it says true or +1. If the number is not positive, it says -1. So if w transpose x plus b is greater than or equal to 0, then the label is plus. Otherwise, the label is minus. Sometimes especially in older papers, you might see pictures like this. A linear classifier is, in some sense, or a linear threshold unit is the simplest kind of a neural network, where you have these nodes that carry features. The edges are associated with the weights. There's one node for the bias. The edge on that is the bias term. If information travels along this edge, it gets multiplied by the weight. So along this edge, by the time it comes to this node here, you get W1, X1, and here you get B. All of these things are added up, and then there is a sign. The linear classifier has a nice geometric perspective in that it's basically representing a hyperplane. A hyperplane, just to remind you, is the n-dimensional or the d-dimensional generalization of a line or a plane. It cuts the space into two parts using a flat surface and says one side is positive. So the picture that we'll always be using is that we have a line and a direction that marks the positive side. The perceptron algorithm is one of the earliest algorithms that was developed for learning such hyperplanes. It was proposed for the first time with this name by Frank Rosenblatt in about 1957 or 58, depending on whether you want which version of the publication you want. But it turns out that earlier instances of this algorithm were also present in previous work in the math literature. In particular, there's an interesting paper of Agmon in 1954, which, if you read through the details, he essentially proposes the same algorithm. The goal of the perceptron algorithm, the name perceptron was invented by Rosenblatt. The goal of the perceptron algorithm is to find a separating hyperplane. And it comes with this really cool guarantee. If the data is linearly separable, the perceptron algorithm is guaranteed to find some hyperplane that separates the positives and the negatives, some line, if you want, in 2 dimensions. It's an online algorithm. It processes one example at a time. And all these online algorithms have the same sort of structure. It sees an example, makes a prediction, and if the prediction is wrong, it makes an update. In practice, of course, when we implement it, we typically don't implement the online version. We will be implementing the batch versions of these algorithms, and those are the ones you are going to be working with in the homework. So let's, without any further ado, look at the algorithm. It's a very simple algorithm. One measure of the simplicity of an algorithm is, can you present it in full detail in one slide? And the Perceptron algorithm definitely fits that. So the input to this algorithm is a sequence of vectors, x1, sequence of training examples with labels. Every example is a d-dimensional vector. It's in RD. It doesn't have to be a Boolean vector. It can be any features. And the labels are -1 and 1. We start off by initializing your weights to the 0 vector in the origin in this d-dimensional space. And then we start processing one example at a time. We first make a prediction, which is the same way we make predictions for any linear classifier. At any point of time, we have some weight vector W. So we make a prediction. How do we make a prediction for this example? We take the dot product of this example with the weights that we currently have, look at the sign of it. And maybe the prediction, we'll call it Y prime. Then we look at the label. The label is Yi. If the label does not match the prediction, in other words, if Yi is not equal to Y prime, that's here, then we make an update. And this is what we will be looking at this in a fair amount of detail. This is the famous Perceptron update. The Perceptron update is, it says, my new weight vector, W sub t plus 1, is my old weight plus, I'll ignore the R for now, it's plus, you multiply the label with the input features and you just add it in. And then you do this till you run out of examples, and then you return the final weight vector. It's a rather simple procedure. So let's kind of look at this in a little bit more detail. The prediction is the sign of W transpose X. Importantly, the linear classifiers are defined by the weights and the bias, and I've not written the bias here. The reason for that is I'm assuming that there is a constant feature that's inside the weights, inside each example, like what was written here. So there is a constant feature. The last feature is always a bias feature. As a result, the last weight is always a bias element. So essentially, the bias is folded inside the weights. A minor side note is I'm using -1 to represent false and +1 to represent true. And this just makes our life easier going ahead. We'll see why in a minute. So let's look at this update. A positive example means Yi is +1. So when there's a mistake on a positive example, what's happening is the new weight is the old weight plus the features plus xi. When there's a mistake on a negative example, the new weight is the old weight minus the features. Ignore the R for now. What this means is after this update, the weights will look a little bit more like a positive example. After many, many updates, the weights will start looking more and more like positive examples because you keep adding them, and less like the negative examples because you keep taking them away. But this has a nice geometric intuition, which we'll get to in a minute. The R is a constant. It's a real number. It's called the learning rate, also called the step size. How much of a step do we want this learner to take every time it makes an update? It's usually a small positive number that's less than 1, less than or equal to 1. Notice that update happens only when there's an error. The update, this is why it's a mistake-driven algorithm. Updates happen only when there's a mistake. And the final comment I wanted to make is there are these 2 steps here. First, you make a prediction sign of W transpose X, and then you check if that's equal, if that sign is not equal to Yi. I can combine them together into this one line. If Y W transpose X is less than equal to 0. Why is that true? You can actually work it out by examining all the cases. If YW transpose, if YI is plus 1 and W transpose X is less than 0, in other words, the sign is -1. So the YI is positive and W transpose X, I'm going to ignore the less than, it's fine, is negative, then there's a mistake. Similarly, if YI is -1 and W transpose X is greater than 0, that means the sign is +1. So yi and the sign have opposite signs, which means the product yi times W transpose X will be negative. In both cases, W transpose X is negative. There are a few questions. Let's see. So just a minor, what I have here is the simplest version of the algorithm. We'll see more robust versions in a bit. So the question, so why is R less than 1? R is a step size. If R becomes bigger than 1, and when you implement this algorithm, I encourage you to play with that idea. If R becomes bigger than 1, it essentially makes the algorithm numerically less. The updates are too big. Every single example will make the weights jump around a lot. And so we want R to be less than 1 in practice, or less than equal to 1. It should not matter for the mistake bound that we'll eventually derive, but in practice, it just makes it stable. Does mistake on a positive mean you falsely predicted a positive? No. Mistake on a positive means yi is +1. The ground truth is positive. The mistake is on a positive example. You falsely predicted a negative on that. All right, so let's now see why this is an intuitive update. So let's consider the case where we have made a mistake on a positive example. What that means is the ground truth y, I'm ignoring the subscripts here, the ground truth y is plus, and the current dot product of the weights and features is negative. The new weight vector is wt plus 1. If r was equal to, if the learning rate was 1, then what does the perceptron update do? It's this case here. W is w plus x. Wt plus 1 is wt plus x. You just add x. Now we can ask, what is the new dot product? We know that the old dot product was negative. The new dot product is, well, the wt plus 1 is just wt plus x, transpose, the whole thing transpose x. I can let the x from outside the parenthesis inside. So you get w transpose x plus x transpose x. X transpose x is a term like x square, which is always, this quantity is always greater than 0, greater than equal to 0. It's the length of that vector. So what we are doing is, when we make a mistake on a positive example, that means the dot product should have been positive, but it is negative. So then the update adds a quantity that is positive. So after the update, the W transpose X becomes more than the previous W transpose X. So we are making it slightly more positive. And we keep doing this over time, this will stop making mistakes. That's the intuition. So for a positive example, the perceptron update will increase the score. I'm calling this quantity the score, the dot product of W and X. Before an update, the score was negative, which is not good. And the only way to make a negative thing better, more positive, is by adding something positive. And that's exactly what the update does. You can work out a similar sort of an intuition also for negative examples. If you don't like algebra, let me give you a geometric perspective, because linear classifiers also have a nice geometric intuition. Imagine that we have this old weight vector, we have this hyperplane, this line here that points in this direction. So essentially what this means, it says this region is positive and this region is negative. Let's say we get a new example. This example is X, that is a positive example. It falls in the negative region of this of the hyperplane, because this region is negative. What that means is the prediction is negative, so there's a mistake. So we have made a mistake on a positive example. The update says the new, after we need to change the weight so that it is the old weights plus yx, but y is +1. So we can now pull out the old vector addition rules that you may have seen, I don't know, somewhere in 3rd grade or something, where this is the parallelogram of law of adding vectors. We just take, we want to add this vector with this vector here, and the answer is this new thing. So what we have done here is we have essentially, the perceptron update says, I want, this was the original weight vector, and this is the new weight vector after the addition. After what we have done here is, but the weight vector controls how the hyperplane looks. So the perceptron update has essentially rotated the weights so that the positive example is more likely to lie on the positive side. Similarly, let's kind of step through the same process with a negative example. Let's say this was the original weight vector, and this side is positive, and the example is incorrectly placed on the positive side. So again, we make the same thing. The weights is weights plus yx. This time y is -1. So really w is w minus x. What is minus x? It's saying I want to add an inverted copy of the x vector. The x vector was pointing this direction. Minus x is going to point in this direction. And we do the same thing again. We apply the same process, and we see that essentially the new weight vector is rotated. Of course, this is an extreme case. This is a extreme case where the after seeing this one example, the vector is, the hyperplane is correct. It need not be correct. It might just be less wrong, and that eventually it will hopefully become correct. So let's see if there are any questions. We use the weight vector for the next example, not the current one. Yes, after the update, we don't have the current weight vector anymore. We only have this new weight vector. We keep updating the W's and using that one. How could we conceptualize this update in the context of the bias term? In this case, yes, that's right. So in this case, the bias term is in the hyperplane is going through the origin. So there are two ways of conceptualizing it. The one way is to think this is not in the d-dimensional space of the features. It's the d+1 dimensional space where the bias term is inside inside the features. Alternatively, the other way of thinking about it is in the d-dimensional space, the way to conceptualize it is you're not just rotating, but also moving the weights around a bit. So it's both rotation and translation. There are a couple of questions more. The weight vector is always pointing towards the positive label. It's not always pointing towards the positive label. That's the ideal case. We want the weight vector to point towards the positive label eventually. In fact, if the weight vector always points towards the positive label, the positive examples, then we have a perfect classifier. The last question, what happens with multiple mistakes? Well, this is just, remember, the algorithm is looking at one example at a time, and currently we have only one example. Once we have this example, then we just, the next example comes in. We have forgotten the old one because all the information about the old one is now inside the weight. So there is no notion of multiple mistakes. This particular weight makes a mistake on one example and makes an update, tosses out the example, then the next example comes in, possibly makes a mistake, makes an update again, and so on. Let's see, there's one more question. Then the update for the negative case can ruin. Okay. So this is I like this question. The question is the update for the negative case can ruin the result because maybe we did the right thing for a positive example, and then the negative thing has ruined what has happened for everything we learned. We have essentially forgotten, to use a metaphor, what we learned, and this is it could happen. Every single update is not going to give us the perfect classifier. All we can say, or all we will say formally, is eventually everything will work out in aggregate. But if and only if the concept we are learning is linearly separable. If the concept we are learning is not linearly separable, then this notion of one example ruining the previous weights that we learned will always happen. And we will prove the first part of this in the next lecture. Next, in the homework, we talk about the batch version. And okay, so let me just, this is a good segue into the next thing, which is a list of variants of the perceptron. So in practice, we don't have an infinite stream of examples that keep coming in. And Brett, I'm going to answer your question once we see the batch version of the perceptron. In practice, we don't have a infinite stream of examples coming in. We have like a fixed training set, like you have in your homework. So how do you use the perceptron algorithm with a fixed training set? And the answer is what I'm calling the standard algorithm, but what should be really called the batch perceptron. And here, the batch, the notion of a batch is really the data set is the batch. It's that we just have a fixed set of examples that we are going to now somehow use to simulate an infinite stream of examples. How do we do that? We are given a training set, D, and we every example is fixed is in I say N here. I should have said D. Every example is a D-dimensional feature vector, and the labels are +1 and -1 or -1. Learning proceeds pretty much the same way. We initialize the weights to the 0 vector. In your homework, I asked you to initialize it to a random point. It should not really matter. And then learning proceeds in multiple epochs. In every epoch, what we do is first we shuffle the data. We shuffle the data set that we have, and then this step 2 really is exactly the same as the perceptron algorithm we saw before. Then we go through every one example at a time in the data set. If we make a mistake, if YW transpose X is negative, then we count that as a mistake. Then we update the weights as W is W plus RYX, exactly the same perceptron update. Once that's done, we are done. Once we have finished this entire batch of examples one time, we go back. We have finished one epoch. Then we start the next epoch. The next epoch, we do the same thing again. We shuffle the data and then run through all the examples and apply the perceptron algorithm. We have this extra hyperparameter, which is how many times do we have to see the data? Once you've seen the data T times, well, not you, but the learner has seen the data T times, you declare learning is done, and you return the final weights. And you proceed with prediction exactly the same way as we did before. Prediction is always the same. So there are a couple of questions. The question from Brett is, I mentioned the batch version, but I don't talk about the batch size. Here, the batch, we have not talked about batch size at all. Here we are just, this is called the batch algorithm simply because we just use all the data. The example just uses the inner loop at all points uses exactly one example at a time, the innermost loop. Do we decay the learning rate? In the simplest version of this algorithm, we do not decay the learning rate. In your homework, I think I asked you to decay the learning rate because that's just another variant. And you do change the learning rate at the end of every epoch for your homework. We have this hyperparameter T that you need to use in your homework. I asked you to pick the number of, set the number of hyperparameters. I just told you to use a certain number. But in practice, you can also kind of think about how to choose that number. All right, so there are 5 minutes left, and that should be enough to introduce the next variant, which involves this really cool idea called averaging. So far, we have always returned the final weight vector. In practice, however, there could be the following problem that could happen. Remember that your learning algorithm proceeds through a series of weight vectors. You start off with your initial weights, and then maybe it survives for a while, and then you make an update, you get W1. Maybe immediately you make an update to W2, and maybe W3. W3 survives for a little while, you get W4. Survive for a very long time. Actually, let me draw this slightly differently. W3 survives for a very long time, and then you make a W4, and you move on. And let's say this is the final weights that you return. At prediction, so the problem is, notice that even though W3 was a weight vector that survived many examples, So this is the number of examples. Our final weight vector is not W3. This was the question. This is related to what Han had asked. Our final weight vector is not the weight vector that was correct most of the time during training, but instead it was the weight vector that was just updated just before the last example was seen. And as a result, this vector W3 that was correct for most of the time, if you count the fraction of examples that each weight vector was correct, W3 was the one that was right most of the time. And yet, it's not the one that's returned. W4 is the one that's returned. And so this means that if there is some noise in the data, and that noise comes at the end of learning, the perceptron algorithm can be sensitive to that. A way to get around that was this notion of a voted perceptron. What a voted perceptron does is, instead of just remembering the last weight vector at each step, or instead of keeping only the current weight vector at each step, it keeps all the vectors it ever encountered during training. And in addition to that, it also remembers how many examples has this vector survived. In the end, when a prediction is to be done, so the final output of the voted perceptron is all weight vectors and a score for each weight vector that says this vector survived these many examples. And when it comes time to make a prediction, what it does is, instead of just predicting the weight the prediction, making the output of the final weight vector, it asks each of them to make a prediction. So in this case, you get 5 different labels, but every prediction is aggregated by weighting it with the number of iterations it survived. That it gets those many votes. So this comes with like strong theoretical guarantees about generalization. But unfortunately, as you might imagine, this is a rather impractical algorithm, because if you're going to have million weight vectors during learning, you will have this just is an untenable proposition. As a compromise, there is a variant of the perceptron algorithm called the averaged perceptron, which instead of using all the weight vectors, it just keeps a running average of all of them, whether you make an update or not. And then you only return the average weight vector at the end. This is a more practical alternative that is usually implemented. So let's look at a few questions. Should averaging start at the start? Yes, it will eventually get it will disappear in the average, so it doesn't matter. There is a question from Thomas. If our hyperparameter was accuracy, how do we stop that loop on that? I don't understand the question. So could you clarify, or maybe we can even move it to Canvas if you don't mind, because I want to actually just go through the averaged perceptron algorithm before the end of today's lecture. It's a rather simple change, so the 2 minutes should be enough. So Thomas, if you don't mind, we can move your question to Canvas. So the average perceptron is almost identical to the perceptron algorithm, except for 2 changes. In addition to all the things that we have an average vector that we maintain, and we just keep a running total. Whether or not you make an update, you add the weight to the average. The average keeps growing, and you have to worry about numerical issues. Doesn't usually come into play, but it can happen. And at the end, you return the average vector and not the W. And the final prediction is done using A. Notice that the error correction and checking is still happening with W. So this is the simplest version. There's a nice programming trick that you can use to make sure that even the averaging update happens only when there's an error. I'm going to leave that as an exercise for you to invent. And if you ever want to use the perceptron algorithm, always use averaging, because it tends to be more robust, because it's more robust to noise. A final variant is called the margin perceptron, and this is also something you're going to implement. Notice that the perceptron algorithm makes updates only when the prediction is incorrect. What if the prediction is correct, but close to being incorrect? So instead of 0, what if it is almost negative, not negative, but like maybe 0.001. So the margin perceptron says, let's have a hyperparameter eta, and instead of which is a positive number, and instead of making an update when yw transpose x is less than 0, you make an update when yw transpose x is less than eta. So the correct prediction is correct, but the point is so close to the hyperplane that you might still want to correct it. And it's worth thinking about why this is an intuitive update. This does not converge to a regression line. This converges to a classification line because we are doing a classification problem. This will not work for, this is not a regret. So this is not the same as regression. All right, so I'm going to wrap up here. We looked at the perceptron algorithm, and in the next lecture, we will look at why this is a good algorithm, and we will look at a formal result that says the perceptron algorithm is guaranteed to converge. I apologize for being a minute over time, but I would like to stop. And please come with questions. At this point, you should have everything you need for your homework. Please come with questions and such things for in the next lecture, or let's use Canvas for discussion. All right, thank you all. Don't forget to get started with your homework if you haven't already. I will see you all on Tuesday.